Καλημέρα και από μένα. Μάλλον πρέπει να βρίσκομαι εδώ. Ευχαριστώ πάρα πολύ τους δύο οργανωτές. Ευχαριστώ πάρα πολύ και αυτό το audience. Είναι λίγο overwhelming, η αλήθεια είναι. Πριν σας πω ποιος είμαι και τι θα κάνουμε, μπορώ να κάνω την εξής ερώτηση. Ξέρω ότι δεν είναι μόνο φοιτητές εδώ, αλλά πόσοι από εσάς είστε μεταδιδακτορικοί φοιτητές? Πόσοι είστε διδακτορικοί φοιτητές? Μεταπτυχιακοί και undergrad προπτυχιακοί. Οκ. Καλώς. Λοιπόν, έχω το ίδιο σχετικά δύσκολο task με τον Κωνσταντίνο, να κάνω squeeze σε μία ώρα optimization. Οπότε έχω παραπάνω από ό,τι χρειάζεται slides, αλλά ξέρω πότε να σταματήσω και ελπίζω να έχουμε μια καλή κουβέντα. Ονομάζομαι Αναστάσιος Κυρillidis, έρχομαι από το Rice University του Houston. This is a Texas session. Μετά το Austin είναι το Houston. Και θα μιλήσουμε για optimization και machine learning. Οπότε δεν θα μιλήσω τόσο πολύ για LLMs, δεν θα μιλήσω για neural networks in general, αλλά θα μιλήσω γενικά για πώς μπορούμε να κάνουμε εκπαίδευση, training αυτών των μοντέλων. Επίσης, ήθελα να κάνω τη διάλεξη στα ελληνικά. Δυσκολεύομαι, αλλά θα προσπαθήσω να τα καταφέρω. Λοιπόν, βεβαίως. Okay. Okay, then I will turn in English. Forget it. So, good, that's easier. Thank you very much. Good. So let me start. And I will start with the theme of the summer school. Okay, so everybody probably knows at least about LLMs. And this is not the very newest, like the newest, let's say, table of LLM models. Okay, let me actually parse it a little bit for you. So what do you see as numbers here is the number of billions of parameters of these models. Okay, so you can see that there are some models that are actually at the level of like trillion parameters. Okay, and as you can see, like computationally, it probably is something very difficult to train. That's why we have the GPUs, the GPU clusters. Like it's not like a game for everyone. Just to give you an idea, and I'm quite optimistic here, if you're going to pick a 7 billion model, language model, okay, so you have 7 billion parameters, you need at least 24 gigabytes of RAM just to ask a question so that you get an answer. Again, very optimistic. And in order to train it, you need at least 56 gigabytes of RAM. And again, this is super, super optimistic. You have to reduce the context, like the quantization, et cetera, right? So in a way, this also like depends on the data set that you're going to use. So training is going to take you a lot of time. And we heavily rely on very specific hardware, which is actually NVIDIA hardware mostly, like the GPUs, the NVIDIA GPUs. We also rely on the software that comes with that hardware. Have that in mind. For example, if you're going to design a new algorithm, and conceptually, this algorithm is very good, it might not be very good when you actually implement it, because maybe the software will not have the capabilities in order to do exactly what your algorithm wants. Okay, so this is where research tries to drive a little bit like what maybe industry or like whoever creates this hardware, they should actually have as functionalities. What I want to say here is like this is a game not ideal for like, let's say, usual guys like us. Like, as you can see, the names of the players are the big, let's say, companies. Okay, so you see Google, you see some universities there, but it's not something that for less powerful player like me, for example, I cannot actually train this model. So in a way, you try to think a little bit like out of the box. So what can we do in optimization in order to reduce the training time, et cetera, et cetera. Okay. So just to give you an idea, someone would say, okay, I hear about LLMs. What is actually a list of things that I have to do in order to actually train an LLM? And it's not like an exhaustive list, right? I mean, you need to select a data set that depends on your application, okay? And I give you here, these are old, relatively old data sets. I give you here some data sets that are actually on the left-hand side for language models. And also there are some other data sets. Here I give the Bloomberg data set, okay? This is our text. There can be also like be some vision. What I want to say here, Some of them, they're actually open source, but some other are actually not open source, which means that it was known before, but now it becomes again, that data is again the new gold. Like if you have data, you have an application, for example, that nobody else has the data on that, keep that if you want to squeeze whatever you can out of it, okay? So for example, Bloomberg GPT is actually an LLM, like a language model, that can answer questions about financial matters. And because it was trained by Bloomberg, they have internally all the articles and all the discussions they had. And that's why they claim to be better than the GPT models from Microsoft and OpenAI, because it is specifically on finance. Okay, so data is quite like important. Of course, it's not like whatever data you have, it's going to be nice. If you have garbage, like the classical, what they say, garbage in, garbage out, you have to clean it, you have to pre-process it, and there are some techniques out of scope. I'm not going to get into there, but I want to say here that one of the reasons that they are also like motivate to go from LLMs to SLMs, from large language models to small language models. I believe like the main reason is like they cannot keep up training bigger and bigger models because it is like not very cost effective for them, for the companies. So they try to say, okay, do I need 1 trillion parameters, or should I have actually a better data set and a smaller potentially like neural network in order to actually get the results that I want, okay? So there are some recent efforts about that, like about like small language models, and I get small is at the level of billions, it's not like small, okay? But I want to say that it's not like the scaling laws that I'm going to say a little bit now, is not that always the only hope is actually get bigger, get big data. There are probably other solutions that can be as effective as that, and also like not as cost ineffective as that, okay? So that's what I was going to say. Also, you choose a model. There is going to be a lot of discussion about transformers, I hope, for this, like during this summer school. I'm not going to explain to you what is a transformer, but it is a neural network, let's say, architecture. Usually, everything is transformers now, like whether it is physics-informed, like neural networks, whether it is like weather forecasting, whether it is NLP, you can actually, like, there are functionalities and modules in transformers that can actually take whatever data in and actually process it in the right way for your task, okay? And there are scaling laws where you actually say, okay, I have that much compute power, I have that many data, that many parameters, what is the right size of the model for the data that I have? And these are empirical. And it doesn't mean that we have to follow them. It's up to you guys to come and say, you know what, this line should not be that, should be like that. But of course, in order to do that, you need the GPUs to test it, and I don't think it's like easy to change these scaling laws unless you're like a big company. Okay, so you choose your model, you choose its size, right? And then you select the hyperparameters, you spend a lot of money and you say, okay, let's hope for the best. Honestly, that's what is happening more or less. Okay, especially if you're trying something new, you just test it, you get like the output, and then from the output you figure out, oh, I should change this to that in order to actually make it work better. Okay, so this is where optimization usually kicks in. Okay, so how you choose your data, it's based on your application. How you pre-process your data, nothing to do with optimization. How you choose your model, nothing to do with optimization, but I will actually, I agree with what Konstantinos was actually saying before, that there is a case, there are like, I think, I'm not sure whether it was actually extensively discussed, but for example, one of the algorithms that we use in neural networks is Adam. Adam was designed, or SGD with momentum. The parameters were designed because it was actually trained on a very specific ResNet neural network on a very specific data set, which is ImageNet. So the parameters, they came from that training, and maybe there is like a cycle, like I have this algorithm, I have this problem, it doesn't work well, how do I change the algorithm to make it work well? And then you get into a new algorithm, but at some point you're going to say, I don't have ImageNet anymore, I have an LP. Should I change the algorithm or should I use the same algorithm? So it's kind of like a cycle that you have to figure out, and do not just use Adam because everybody's using it. But I'm going to say also Adam is based on principles of optimization, that it has more foundational, let's say, it has like more fundamental, let's say, underpinnings that why they actually use Adam later on. Okay, so how do we train a neural network? Okay, let me actually get to that. So optimization, usually we talk about minimizing a function, f of x. You're going to see a lot in the literature that your parameters are W. I come from a more classical optimization, let's say, background. When I was actually a PhD student, that was the time where more or less like neural networks were actually getting into like machine learning a lot. So I usually have x as the parameters, but try to adapt. X is going to be, if you want to think about it as W, think about it as W, okay? And there are some constraints. For example, Konstantinos was saying like, you might constrain your parameters to actually have a small L2 norm because I want to regularize it, right? So some examples very quickly. Least squares, for example, is a classical convex optimization example. It has applications not in machine learning only, like it's solving the system of linear equations, right? But it's also what it is called the linear regression. This is how the optimization looks like. You have some data. The data here are the responses yi, and the ai is actually the input, and x is actually your inner parameters that you want to find in order to minimize the summation over the data n samples that you actually have. Okay, but optimization also looks like more complicated for neural networks. This is not a complicated neural network. This is more like a fit-for a neural network, right? Where you have your input, and this is where it gets weird. X now is the input because my W's are actually the weights, right? So you have your input X, W's are actually your optimization parameters until you get the output, and the final result is actually you want to minimize a function, which is a summation of functions, of loss functions, where now it can be complicated. Like your output is going to be like the forward propagation from your input through the parameter, some nonlinear activations until the output, and then you compare it with your true labels. And then you try to minimize the loss. How far are the outcomes, the predictions from the true predictions? That's the training, let's say, procedure. Okay, so going back to that, I want to ask the following question, and I don't have the time actually. You have a one-dimensional problem, okay? There is like on the x-axis are the parameters, on the y-axis is the function values. And you want to actually, and someone gives you the initial point, x0, right? And you want to minimize the function f, right? This is what a computer knows at the beginning of the training. I'm here, and I have no idea whether I should go left or right. This is what I see only, okay? So whether I should go left or right and how bad this function looks like, I don't know it. So the question is like, what type of information I can locally extract by interacting with the function f of x, but I cannot ask questions given that I'm at the point x0, something that happens far away from x0, okay? So the function might look like that. So if you predict it to go left or right, actually the minimum is exactly here, right? So, oh no, wait, I'm here. So it's actually here. So if you started from there, you might be at a point that you say, oh, it looks promising if I move a little bit here, and then you're stuck to a local minimum here. If you start going this way, you might say, oh, this is not promising, but what the hell? Let's actually go that way. You might get into weird positions, and I'm not going to talk about this. There might be discontinuities, actually not, but you have to remember that neural networks also have like components that they might be not discontinuous, but they might also like have non-smooth, let's say, components. But in any case, it's not trivial to get from here to there without looking like the full picture. Okay, so this is what differentiates between the nice and the not that nice functions. Like nice functions are least squares functions, convex functions as we actually call them, because they look like a ball, and wherever you start, you actually, most probably, you're going to get to the bottom of this bowl by following some information locally from your function. Okay, we're going to talk about this later on. The more difficult functions is when you go, for example, to neural networks, and now the landscape looks like that, where you might have pockets of local minima here and there. You might have many of them being equivalently good. You might have a very good global minima somewhere, but you don't know where to start and how to get there, because you don't have the picture. This is a two-dimensional problem. Now think of like 1 trillion parameters. There is no way even for 4-dimensional problem to show and illustrate how the function looks like, right? I mean, we are restricted in 3 dimensions. There are some techniques, I'm not going to say there, like if you want to look around, there is like Google for visualizing, let's say, energy landscapes of neural networks. And there are some people are trying to figure out how I can actually visualize how the neural network looks like, even if it has like millions, billions, or trillions parameters. Okay, so how do we train? How many of you know gradient descent? Okay, cool. So at the very end, the short story is that you assume your function is smooth, meaning that at every point you can compute a gradient. Gradient is about, like, gives you information locally, how, like, the slope, like if this way goes down, that way goes up, right? We get the negative of the gradient because the gradient always looks upwards, so you get the negative to minimize, right? This nabla f, at the very end, you can think of it as a vector, the same size as the number of parameters that you have. And then you say, given my current model, xt, my current trained model at the time t, I want to update that based on the negative of the gradient multiplied by eta. Eta here is actually eta. Damn it, I'm in Greece. In eta, which is actually the learning rate or step size. And then you get the new model at the new time step, t plus 1. And then you keep doing that. That's the idea of training. Okay. If someone wants to know more about how you get the gradient descent, there is a mathematical, and not the only one, description of that, which actually comes from, you're actually at a point on your function. You can approximate your function with a Taylor expansion, the first or the second, and then from that you can actually figure out what is the best direction to move to. And actually the best direction is actually the negative of the gradient. Like, there is a mathematical, it's not like someone thought of it and just fall out like of the sky. It's more like there is a description why this happens. Okay, so gradient is about, I'm at a point, I can compute a local information, which is actually the gradient derivatives, how all the parameters change if I move a little bit from the current point to understand which direction is more promising, right? You compute that, and then you say, my next point is going to be my next train model at the time t plus 1 is the previous one plus an update. The delta t is the negative of the gradient times a step size, which is eta. We're going to talk about this eta later on. Okay, any questions so far? I know I'm limited in time, but I would like to have like any questions thus far. Okay, very quickly, a question up there. And if I screw up the way you guys are working, sorry for that.
I can actually shout.
Please do.
Okay, so with this descent, does it locate total minimums or just local minimums?
The way we define it so far, it will just find a point, and I'm not going to describe, where the gradient, it will stop where the gradient becomes 0. Which might be, for example, let me actually depict this here. Let's look at this picture here. Where the gradient is 0, you can think of it as where I can actually draw a horizontal line, and this is going to indicate my gradient. So this is where my gradient is going to be 0. This is a local minimum. This is going to be where my gradient is going to be 0. This is a global minimum. But also, this is a point where my gradient is 0. This is what it is called the saddle point, because it looks like a samari, a saddle of a horse, right? And this is also a point where the gradient is 0, and it is actually a local or a global maximum. So gradient descent up to this point of this discussion will just tell you what is the most promising locally to minimize my function, but I cannot guarantee it's going to be my global minimum or whether it's going to be even a local minimum. Make sense? Good. Last question, I'm not going to, yeah, please.
No worries, I can solve the problem. So this is highly dependent by theta, right? I mean,
Yes.
We can miss, let's say, the global maximum.
Yes.
Local maximum.
Yes. We're going to discuss about this later on. Okay? So for this, like, sorry for that, Yorgos. So just want to make sure that everybody's on the same page. So given that, right, we can actually see how gradient descent looks like for some classical problems, least squares, right? And I can describe this through modules. Bear with me, okay? I can actually say that this function up here can be split in the following sense. I actually have a module which takes the input AI here and multiplies with my inner product with my model. This is the inner product between two vectors. And then I take this output and I actually plug it into another module, which is I take the corresponding true label and I compare it with the output of that. So if you want to see that, the data here for the least squares is that I plug in AI or alpha I. It goes through the first module. If you turn your head, it's actually the inner product of AI transpose X. And the output of that is going, which is yi hat, is going to compare it with a true label. Okay. The reason I describe this in this modular form is because you're going to see later on that this is the way neural networks are actually defined. You have modules, and you actually see how the information from the input propagates until the very end, which is evaluating the loss function. And based on that, we're going to see that this is the way gradient descent is computed, because I see, oh, my loss function is quite high. I would like to minimize it. What would be the changes that I need to make at every point of back propagating in order to actually make sure that I at least reduce the loss? Okay. So what you're going to do is like, I'm just saying that this function is a composition of functions. And the composition of functions, in order to compute the derivative at the very end, you actually compute the derivative with the chain rule of derivatives. So you actually want to compute the gradient at the very end, and then you say, oh, at the very end, I'm not yet to the source. I have other layers before me. And I keep doing that, where mathematically it might look exactly what you're going to do like on paper, but it actually tells you that there is another way of maybe prototyping, like a coding, how you can actually compute like the gradients. Okay, that's a chain rule of derivatives. And this is the main idea behind backpropagation, which I'm just claiming is nothing else but gradient descent. Okay, backpropagation is an efficient way in order to compute the gradient, because you understand the structure of your function. It is modular, it has layers after layers after layers. So gradient is the backward layer-wise propagation, which means that I have to respect that, and maybe there is an efficient way not to compute it like naively and maybe do double work, but maybe I can do it in an efficient way. So that's the backward pass, and even if you do gradient descent on least squares for MATLAB, still you're doing backpropagation in a way. Okay, so how does this look like for MLPs very quickly? Again, you have modules here. The modules, if you want to think about the yi hat at the top, is the output of your model, right? It's like you have an input xi here. Again, sorry for the switch. Xi is your input. W1 and W2 are the two weight matrices of your model. And then you get at the very end the yi hat, the output. So I have the following modules, which is like, first you have this module, which says that given xi, I will just pass it and multiply it with a wi and then have a nonlinear activation function. That's module number one. Module number two is take this, sorry, that's a typo, phi1, multiply with a w2 and then have a nonlinear activation function. So this actually looks like that. Still modules, right? So you actually have the input, And then it goes through phi1, phi2, then there is a softmax, another function, and then you get actually the output. Again, chain rule of derivatives, backpropagation, like that's what I want to tell you when you go to PyTorch and TensorFlow and then you pick your optimizer and then you say train or whatever, then you actually, you're under the hood, there is code that does that for you. That's the nice thing about PyTorch. We used to compute exactly the gradients on paper and then code them up in order to see whether we actually can do gradient descent in a nice way. Now you actually define the function, and as long as the function satisfies some very mild, let's say, assumptions, probably you are just like one line away from running an algorithm in order to train it. Okay, make sense? So for me at least, when we talk about backpropagation, it's more like ways to do gradient descent. Okay, and we're going to discuss about that later on. So one of the ways that we do gradient descent is actually stochastic gradient descent. And most probably is the algorithm that you're going to use or you're going to definitely know about when you're training neural networks. Okay, so as Konstantinos said, in neural networks and in general in machine learning, my function is a summation of functions, where the summation is over the training data that I actually have. I actually try to minimize the sum of the losses over all the training data examples that I actually have. Okay, it's the sum 1 over n summation of the loss, where n is the number of like examples. When you do, that's your function, your empirical risk minimization, and when we talk about f of x here, is the empirical risk minimization. It can be f of theta if I want to continue with what Konstantinos had. Okay, now, so far I'm just saying compute full gradient descent. Take all your data, and you actually compute the gradient over the full training data set. And that's what you see here. When you just see gradient like this, it means that I'm going to use the full data set to compute the gradient and then do a step. Now imagine that your data is, even if you think about like ImageNet, which is a super small, in a way, data set right now, the small n, the data examples, is at the level of 1 million images, which means that if I want to compute one step, actually you have to go over 1 million images, compute the gradient before you go to the next step and you do it again. So first of all, it's super inefficient to do that, but there is also like statistical reason not to do that. And it's up for discussion whether this is true or not, but we can actually discuss it later on. So what is the solution to that? Stochastic gradient descent. Instead of taking the full data set at the current point to evaluate your function and then do the gradient step, I can actually pick 10 examples and see whether my model works well on these 10 examples, and if not, how much I should actually change the parameters. So that's the notion of stochastic gradient descent. I pick some of my data points in order to compute the gradient only on these data points, mini bats, as we say, that we picked. Okay, there are reasons why you're gonna do this. It was back in the days in the 2000s where we were talking about, not me, about like big data era, where the idea is like, if I have so much data, I don't want to go over all the data in order to make progress. Maybe I can see part of the data set in order to make progress. So instead of computing full gradient, you're actually saving a parameter of the level n, okay, in terms of like complexity. But there are other reasons to do that. We're going to see later on. It's about generalization. Like if you do full gradient descent, most probably your model is going to overfit, or it might get stuck to a local minima which is far from the good local minimas, and then it's not going to generalize well if you ask it questions on data that it hasn't seen them before. Okay, so it's very important for this talk to follow my hand. Follow. Okay, you're not sleeping. I usually do that at my class so that I wake up people, because I know it can be boring at some point. So that's the difference between gradient descent and stochastic gradient descent. What you see here on purple, again, this is not neural network, this is just like a least squares problem. Okay, what you see with the contour lines, think of it as a ball that gets out of the screen, right? and you want to get to the bottom of that, which is the very small circle in the middle. And you start at the bigger, let's say, contour, and you want to go to the middle. What gradient descent does, which actually says that I will take all my data and try to do gradient steps, you see how steady it goes towards the minimum. It's actually perpendicular to the contour lines because that's the best that it can actually do given the, let's say, the local information. The cyan blue, the curly one, is stochastic gradient descent. It doesn't use fully all the data that it has, so it doesn't see the full function that it has to optimize. Think of it like that. Like if your function f has 1 million images, stochastic gradient descent at every point thinks, oh, my function has only 10 images, that's my function and that's how I'm going to optimize at this point. In the next iteration, it has another 10 images, then another 10 images. That's why it doesn't know exactly where to go, but on expectation, as we say, it will actually go closer to the minimum that we're looking for, okay? So, I'm not going to go over all this. I was trying to think, okay, I was given the task optimization in ML, and then I said, okay, there are different things that someone can say. One is, for example, and maybe we talk about it, is the training algorithms. We talked about gradient descent and stochastic gradient descent. Someone would say, oh, I'm not using that in neural networks, what this guy is actually saying. I know about Adam, I know about momentum, and this is not there yet. So one is training algorithms, two is about theory, and I'm not going to get too much into theory, but how optimization theory helps machine learning in order to prove how big your neural network should be in order to guarantee convergence, right? So over-parameterization, as we say. Okay, under which conditions, et cetera, et cetera. There is hyperparameter tuning, the question about learning rate and step size, and definitely other areas that I'm not going to talk about. There are optimization-driven solutions. For example, there is like now a call in NSF, the agency in the US, where they say mathematical foundations of AI. And I think that one of the things that they have in mind is like in the 2000, one of the successes of, let's say, engineering, mostly in computation engineering, was compressed sensing. Not because it was actually impressive, necessarily. It was impressive because somehow we could solve linear system of equations with less number of, let's say, observations than unknowns. But it was the idea that Terence Tao and Candes and Romberg, like applied math statisticians and mathematicians and engineers, all together, they actually said, this is the way to solve the problem. I think that for AI, we're looking for a similar situation where statisticians, engineers, applied mathematicians, computer scientists, they're going to actually look for solutions why this happens. And I'm just saying here that sparsity, for example, originates far from neural networks, but now it's a big thing in neural networks because you want to prune how many parameters you're going to keep, right? And how do you learn features? Do they live in a low-dimensional subspace? I'm not going to talk about this. I'm not going to talk about large scale. I think that Dimitris is going to talk about that. There is also a notion of like games, which is the idea used to be for GANs, but now we have the diffusion models. But I'm also skeptical about like optimization is not everything. Of course, there are other ways that you can actually do optimization, okay? But I'm just saying like this is what has prevailed and this is how we actually train neural networks, okay? So training algorithms, and I will try to be short here. So impossible task to explain all of them. Because in 2021, there was a paper where the algorithms were that many, wait for it, that many, wait for it, that many. That's a paper that I'm not sure whether they compared them, all of them. There is also like, I think MLPerf is like an online benchmark. I know at least one author, like Michael Rabat from Facebook, where they have a series of like non-trivial optimization tasks, machine learning based. And they say, in order to avoid all these things, like going over all these algorithms, upload your algorithm and compare with the best of a leaderboard. So it's more like a Kaggle competition, okay? So that's back to 2021. Everybody had a new, I also had like a version of that. But I think that I'm just saying to you guys, if you're going to design a new algorithm, be aware that you have to convince all these people that you're better than them. So it's a little bit like tricky. Okay. But there are some common practices, and I will go over them very quickly. One of them is momentum and acceleration. Okay. You might have heard the name Nesterov. You might have heard the name Polyak or heavy ball method. The idea is like instead of just using the gradient information to move over the landscape, you're actually doing something else. Like the purple line is like gradient descent, and it's kind of like going like, someone would say that why does it go up and down, and why doesn't go like directly to the minimum? It is because locally at the point that it computes the gradient, the most promising direction just happens to be almost perpendicular to the direction that it wants to move. Okay, because the contours, like the slope at this point, it actually tells you go back and forth like this, and that's the best I can actually give you. The blue one is something else which is called like momentum. It actually tells you like, given that you do this all the time, I feel like there is a momentum that you want to go that way, so maybe I can use this information to go faster in that way. Okay, so what is the idea of momentum? It's like that was like gradient descent, only the first part, right? That was the gradient descent, that's what we talked so far. But there is something that you add, that's the simplest way to do like momentum, right? Where you don't only rely on the current point, but you also rely on the previous point at the xt minus 1. So here, in order to understand this, this is the model, 1 trillion parameters model at the point like time t, 1 trillion parameter model at the time t minus 1 in order to generate the t plus 1. Okay. So in the old days, it used to be almost like no cost to actually do this addition, because you can think of it like that's a vector, that's a vector, that's a vector, that's a vector. I only add a vector to a vector, so that's kind of like cheap, right? But can someone tell me very quickly, if you raise your hand, what's the problem with this? Like, what is the downside of using momentum compared to gradient descent? 3, 2, yes, shout. No. Memory requirements. So gradient descent says that I have my current model and I just have to compute one more gradient. That's a 1 trillion plus 1 trillion. If I have a memory that can handle 2 trillion parameters, I'm fine. But now you have to keep in memory the xt minus 1. And if your GPU doesn't have the memory to do that, of course 1 trillion is impossible for a GPU, but I'm just saying, like, think of a scenario where this can break, right? But there are like downsides. This way, why someone would do momentum is maybe you train faster. So there is a faster convergence rate, but the downside, the trade-off, is that you have more memory requirements. So there is kind of like something that you have in mind. Okay, so why does this work the way that it was working in the picture is the following. You're at the point xt minus 1, and let's say through the algorithm you go at the point xt, which is the new point, right? Then you compute the gradient, the negative of the gradient. That would be the point that gets you with gradient descent, right? But momentum tells you, forget about only the gradient. I know that going from xt minus 1 to xt, I was having a momentum in that direction. Can I use this information also on top of the gradient? So what you do, you take this vector, you multiply it with beta, which is the momentum parameter, usually set up as 0.9, for example, in your PyTorch or TensorFlow, let's say, implementation. You add that, and that's the new point that it is, let's say, better than gradient descent because it goes in the direction that the momentum tells you, okay? So very quickly, the other thing I want to say very quickly is the fact that there are ideas that come from optimization from second-order methods. If you know Newton's method, that's the idea of the second-order information. I compute Hessians, second-order derivatives. It's the, like, there are some downsides for that. That's a classical way of solving, let's say, linear system of equations. Newton's method solved it like in one iteration, right? It was informed by Petros about the physics-informed neural networks. That's a way, that's a method that second order information has shown to be better fit than gradient descent, okay? So the idea is like, instead of just computing here the gradient, maybe I can compute another matrix that I can change the direction of the gradient like vector in order not only to locally figure out the slope, but maybe understand like, let's say the curvature generally like around the current point, okay? So that's the idea of like, you approximate the inverse of the Hessian. Classically, there are ways to do that, but that was the main motivation, and I'm I don't have the time to go to that, like to go to the Adagrad algorithm. That's a 2011 paper, I think, by Google, that was later on very much popularized by Jeff Dean from Google for a large-scale implementation, that they found that Adagrad was an algorithm that it is better than SGD, and people should actually use it. And the idea, very quickly, is that instead of just computing a step size eta, right, you also have to use another type of information that comes from the second order information in order to change component-wise for every component of 1 trillion in order to have a different learning rate. Okay, so there is some, like, why should I use the same step size, which is a scalar, like a single number, for all the directions? That might not be efficient. So what these guys are actually saying, you should actually use different numbers for every component, and maybe there is an adaptive way in order to do that that comes from the problem itself. You compute second order information approximately, and you actually do that. Okay. There are some, and again, I'm going to skip that. I don't have the time to do that. Adagrad and using this kind of information led, and this is how it actually looks like in a pseudocode, and I want to get there, to Adam. So what we have been using a lot is Adam. And what Adam does, let's actually focus on the following. It's kind of like a gradient descent method. So MT here, focus only on here, is a weighted average of previous gradients and the current gradient. And there is a scaling of the step size that comes from the second order information. Okay, so you take the approximation of the Hessian and you use that. And that's kind of like the definition of of Adam. It has some hyperparameters that usually you'd never play with them because they actually did so many experiments that they actually work really well. Okay, but again, you have the question marks. Why? Because they do. There are some results that they say Adam converges. There are some other results that they say Adam does not converge. And that's how optimization theory and research has moved on, by trying to find corner cases. Oh, it fails. Oh, it succeeds. That's the case. And that's how we actually, for example, now we have Adam W. They said that that's the Adam, by the way, without the purple and the green box. If you remove this, that's Adam. But they said that I want to make Adam better by including the regularization that Konstantinos had in different places as my objective. And that's the way I get from Adam to Adam W. And the thing is, like, for some of the cases, surprisingly, the algorithm performs much better. So it's not like a small change that someone would say, oh, you just changed 2 points and you're fine. Like, if you show that you're much better, people are going to appreciate that. Okay. So that being said, I think that I don't have the time. I wanted to go into a little bit like into theory, where there you're going to see things can be more creative, almost to the level of proof-enabling assumptions. Like, we make assumptions in order to satisfy our ego that maybe we can prove something about neural networks, but the assumptions themselves, maybe they're too strict that they do not actually live in the real world and they're not actually practical. With that, I would like to stop here, but the slides are going to be available for you. Thank you very much, guys. I'm open for questions.
Thank you, Tasso. Questions? Thank you for. There's one hand over there.
I come from a mostly different background, but I've had some courses in optimization, and I wanted to ask, in terms of machine learning and neural networks, can we use derivative-free algorithms? Have they been used successfully? Yeah.
Yeah, so derivative-free algorithms are the algorithms, for example, where you only ask questions to a model. You never do the backpropagation. You only ask questions, you get the output, and you say, oh, for that question, my output is actually what I expected. Cool. It's not what I expected. Maybe I can use this function evaluations to actually do derivative-free optimization. So first of all, there are different ways to do derivative-free optimization. Before I start with that, if you can do function evaluations, right? The reason that you cannot do derivative, like you cannot do backpropagation, there are many reasons for that. For example, if you use ChatGPT, you can ask questions. You get the output, but you cannot do backpropagate. Like that's the black box. That's property of OpenAI. You don't get to see what is inside the black box to do the backpropagation. That's why we're very, like the community talks about open source models. Llama is an open source model because you can see all the parameters, you can take it, do backpropagation if you have the GPUs, and it is open source. Like, that's one case when you can do derivative free. People have tried to do that. There are recent results about how you can actually do that. Because if you can backpropagate, the backpropagation is not that much more expensive than forward, like by asking questions. It's only a constant time more than doing the forward. But I understand there are cases where you can only ask questions forward. As long as you have informative answers, you can use these function evaluations as numbers in order to approximate the gradients, but you have to pay other things there, like how fast your algorithm converges. Now it depends on the size of the model, and how many iterations you need depends on the size of the model. That's what you pay when you go to the derivative-free optimization. So the short answer is yes, but probably it's going to be even more painful to do that. That's the, yeah.
Thank you very much for your time.
There's another question here.
Hello. So in the Adam W optimizer, the W, it's tunable.
Yes.
Do I put it myself as a hyperparameter?
For now, it says at the very top it's given.
Okay.
So I haven't followed whether there is an adaptive way to do Adam W with adaptive W. And again, sorry guys, like here X, now we go back to my notation, and W is just a scalar, that it is the lambda that Konstantinos had in the L2 norm of the theta. So it is just a scalar that you actually have to optimize or figure it out, and you have to Google, figure out whether someone has done it. If not, it might make sense to actually tune it. Yeah.
So it's a hyperparameter?
Yeah.
Okay, thank you.
Thank you. Other questions?
So, since we can see that there's an issue trying to find out where should the algorithm look for our minima, is Bayesian optimization relevant in this field?
I'm sure it is. I'm a non-Bayesian guy. I don't know the literature there. Definitely the Bayesian optimization has helped in the theoretical understanding of neural networks because they connected with Gaussian processes, et cetera, et cetera. There are hyperparameter HPO based on Bayesian optimization, but it's not a battle. I'm just saying there are two words here. One is more deterministic, the other is Bayesian.
Okay.
We both try in a way to figure out what is the best way to do it. There are automatic ML approaches which are more deterministic. They're more like Bayesian. I'm not saying that one wins over the other. It depends on the case, on the, yeah.
Okay. And if I may, a second question.
Sure.
Since, as you can see with Adam, we can modify algorithms a bit. Is no freelance theorem for optimization still relevant? Does it play a role at all?
Definitely. Like,
Okay.
that's what I believe. Like, you try, you see whether it helps or not, and yeah, I mean, you live with that idea. So you lose something, you gain something. Like, yeah.
Okay, great. Thank you.
Thank you. Other questions?
I can say something on the stochastic optimization, Bayesian optimization. I've worked on a method called covariance matrix adaptation, evolution strategy. The problem with these methods is they don't scale well for large dimensions. And usually, effectively what they do is they try to formulate a covariance matrix, the second order information. That's what more or less they try to form. And for that, if you have n dimensions, the number of iterations goes like n to the fourth. Now, if you have a neural net with 1 trillion parameters, forget it. So that's the problem, and I think the things that Tasos presents are more effective in this particular case. You are limited by the size.
We still have time for 1 or 2 questions. Yeah, I think we can call it lunch. Thank you very much, Tasos.